Hi everyone and welcome to this Circle Theorems revision lesson. So over the last couple of weeks we've done all the work for circle theorems. Now I'm just going to run you through the review questions and talk you through them so that then you can have a go at the knowledge recall for chapter 20. So as our starter then, let's just have a recap through each of the circle theorems. So the first one is the angle in a semicircle is always 90, so always look out for a diameter, and then if we've got a triangle with the third point on the circumference, this is always 90. The next one, the angles at the circumference that are subtended from the same arc. So remember, subtended from the same arc means these 2 points A and B are the same. So we've got an angle that subtends to the circumference here, and it comes from the same 2 points A and B, and here as well. So these are equal because they are in the same segment. So these are equal. The next one, the angle at the centre is twice the angle at the circumference. So my points are A and B again. So I've got my point coming out to the centre. So this is my 2x. The centre to the circumference, so this is half of it. So the angle at the centre is half of the, the angle at the circumference is half the angle at the centre. Cyclic quadrilateral, remember the opposite angles of a cyclic quadrilateral, they add up to 180 degrees. This one, the angle between a radius and a tangent is always 90 degrees. I'm just going to jump over to this one here. Any tangents coming out to meet at a point of contact outside of the circle, then these tangents, these lengths here are equal. And the last one that we did was called the alternate segment theorem. Remember, a segment is a piece of a circle which is enclosed by a radii and the remaining arc around it. So within this segment, it's the angle between the tangent and the exterior of the triangle. So this angle here is equal to the angle inside the triangle in the opposite segment, in the alternate segment. Okay, so this segment here concerns all of these angles, so this is the alternate segment, so the two green angles are equal, or similarly we can look the other way and the two orange angles will be equal. So our success criteria then, hopefully you know and recap the basic angle facts, to recall and use all of the circle theorems that you looked at over the last couple of weeks, and we'll also go through a couple of formal proofs in some of the revision questions. So it's entirely up to you if you want to just look at the review questions, which is in the folder for this week's work, and have a go. The answers are at the end of the PowerPoint, or they're all the way through the PowerPoint, or you could just watch me talking through them and pause the video as you go to see if you were correct. So let's look at question 1. In each diagram, O is the centre of the circle. Write down the value of X for part A. Write down the value of Y for part B. So this one then is the angle at the centre is double the angle at the circumference. So that means then that X must be half of 88, which is 44. So X is equal to 44 degrees. Here, hopefully you're using the angle in a semicircle is always 90 because this is a diameter. So this is a right angle here. So this is 90 degrees. So if we do 90 plus 38, which gives us 128, and if we subtract that away from 180, because the angles in a triangle sum to 180, then that gives me then that Y must be equal to 52 degrees. Part C. Calculate the value of T, stating any assumptions you have made. Okay, so here then, it looks like we've got a quadrilateral, a cyclic quadrilateral, but this point here isn't on the circumference, so we can't use the opposite angles sum to 180 because that's not the case here. So looking at this then, but we have got the same 2 points, and we've got an angle at the circumference and an angle at the centre. The only difference is it's this one which will be double the 110. It's always the one underneath. So 360 subtract 110 would mean that this angle here was 220, which means if we subtract that from 360, that means that T must have been equal to 140 degrees. And the 3 points, not the centre, are touching the circumference is the assumption that we made. So we couldn't use that the opposite angles were equal to 180 here. Question 2, so part A, write down the value of A, and part B, write down the value of B. So here then, we've got angles in the same segment, so hopefully you can just see that A should be 55 degrees here. And this one, we have got a cyclic quadrilateral this time because all of the points of the quadrilateral are touching the circumference. So taking 185 from 180 would mean that this is 75 degrees. Question 3. A, B, C and D are all points on the circumference of a circle, centre O. Explain how you know that the value of X is 160 degrees. Well, we know that the angle at the centre is double the angle at the circumference. So that must mean it's 160. So angle DOB, so using the 3 letters for the notation, so D to O to B would be this angle X, is double DAB, and that's lovely as an explanation. Then part B, give a reason why Y is 100 degrees. So hopefully now you can see if we use the whole of this, we have got a cyclic quadrilateral, so A and C must add up to 180. So Y must be 100 degrees since it's a cyclic quadrilateral, and DAB and DCB must add up to 180 degrees. Question 4. A, B, C and D are all points on the circumference of a circle, centre O. Show that OBCD, so this quadrilateral down here, could only be a rhombus if X was equal to 60. So if we think about what a rhombus is then, so a rhombus must have, I'm not going to be very good drawing freehand this, a rhombus must have 4 equal sides, and this angle must be equal to this angle, and this angle must be equal to this angle. So if this is going to be the case, well, let's think about this first. Let's start with what we've got. So we've got X here, and this is an angle at the circumference. So this angle down here must be 2x because the angle at the centre is double the angle at the circumference. Now let's think about what this will be. Well, this is a cyclic quadrilateral, so these must add up to 180. So that must mean that this angle down here is 180 subtract x. Now if we think then, if we want this to be a rhombus, these must be equal to each other. So if I set up an equation that 2x is equal to 180 subtract x. Now this is unknowns on both sides. Let's take the x here and let's add x on. So let's balance. So we'd get that 3x is equal to 180. So that must mean that x is equal to 60 degrees as it wanted here. How did they set it out? So to be a rhombus, DOB must equal DCB, so we knew these had to be equal. We know DOB is 2x, so that's double DAB, which is what we labelled on here. As ABCD is a cyclic quadrilateral, so and then we've got these must be equal, so this is us setting up the equation and showing that x must be 60. Question 5, PQRT is a cyclic quadrilateral again. ATB is a tangent to the circle at point T. PQ equals RQ, So PQ and RQ are the same length. This is why they have lines on them. Angle RTB, R to T to B, is equal to 42 degrees. So if PT is parallel with QR, so let's just put arrows on. So PT is parallel with QR, show that angle PTR, P to T to R, so we want to show that this angle starred here is 84. Okay, so I don't want to write it on and work backwards, I must start with what I've got. Now I've only given the 42 here, and this looks like the alternate segment theorem. So this 42 here between the tangent and the chord must be equal to the interior angle in the alternate segment. So that would mean that that angle there is 42 as well. Now looking here, I've got parallel lines and I've got an alternate angles here. I've got a Z. So by alternate angles in parallel lines, that must mean that this angle here is also 42. Now you notice we've got an isosceles triangle, so this must also be 42 because the base angles of an isosceles triangle are equal. So here, if I sum these together, I will get 84, and if I subtract that from 180, I get then that this angle is 96. Then I can use the opposite angles in a cyclic quadrilateral, add up to 180. So that must mean that this angle is 84 degrees here. Let's see how they've formally written it out. So TPR equals 42. So yes, I've labelled that here. Now if this was an exam question, they would give you the mark if this was what they wanted here. You wouldn't need to formally write it out. They would label it and mark it as you've done on the diagram. But they might have wanted the reason. So didn't ask for the reasons in this question, but sometimes they do in an exam question. So if they do ask for the reasons, you can just state by the alternate segment theorem. Then P to R to Q is 42 by angles in parallel lines. Yeah, that's what we did. The isosceles triangle PQR must mean then that these base angles are 42, so this is 96, and then they've used opposite angles in a cyclic quadrilateral. Question 6. PD and TD are tangents. Okay. And they meet at an external point here, D. Eve calculated X to be 41, show that she is correct. Okay, so I don't want to write 41 like I've said before and work backwards. We want to work with what we've already got. Now looking here, I've got a radius meeting a tangent. Now I know that they must meet at 90 degrees. So that must be the same over here. I also know that these are equal because it creates symmetry, two tangents meeting at an external point. I know here I've got a quadrilateral, and I know that the angles must add to 360. So that must mean then, so if I do 90 plus 50, subtract that from 360, that gives me that that angle there is 130 degrees. Here I've got angles on a straight line which must add up to 180. So 180, subtract 90 and subtract 66 leaves me with 24 degrees here. Now this is the centre. I've got two radii here, which must mean these are the same length. So I've got an isosceles triangle here. So both of these base angles must be 24. So now I can work out, so this added together will be 48, and if I subtract that from 180, that gives me that this angle here is 132 degrees. Now angles round a point add up to 360. So now I know then if I add these together, I get 262, and if I subtract that from 180, I get that this is 98 degrees here. Then I've got an isosceles triangle again, so 180 subtract the 98 gives me 82 degrees, and dividing that by 2 comes out that x is 41 degrees. Let's have a look how they worked it out. So they've said that CAO must be 24. Yeah. And they've got the 130 here. So yeah, they've kind of done it in a similar way. If the question wasn't asking for reasons, then by just showing the angles on the diagram, you'd be okay. Now it does say show that she is correct. So you might have just wanted to have put a little bit of reasoning down as well. Question 7. On the diagram, lines AB and AC are both tangents of a circle centre O. The tangents touch the circle at B and C respectively. Prove that the quadrilateral ABOC would always be cyclic. So we want to prove that the opposite angles add up to 180. Well, we know a radius meets a tangent at 90 degrees. So I know that both of these are 90. Now these are opposite angles, and look, they add up to 180. So these must also add up to 180 because the angles in a quadrilateral add up to 360. So formally writing that out, OCA is 90 and OBA is 90, as AB and AC are both tangents to the circle centre O. This is a pair of opposite angles having the sum of 180 degrees. Since the sum of the angles is 360, the other pair of angles will also add up to 180 degrees. So both pairs of opposite angles sum to 180, hence it is a cyclic quadrilateral. Question 8. A and B are 2 points on the circumference of a circle centre O. PT is a tangent to the circle at point B. Angle ABP equals x. Prove that angle AOB will always be 2x. So looking at this then, a radius meets a tangent at 90. So that's 90. So also these angles here must be 90. So within this isosceles triangle here, that angle there must be 90, subtract x, because the x plus the 90 minus x must add up to 90. So that would also mean that the opposite base angle in the isosceles triangle is also 90 minus x. And we know that the angles in a triangle sum to 180. So if I've got two lots of 90 minus x, well, that is equal to 180 subtract 2x. Now I want them to add to 180, so that must mean that that angle there is 2x, because I want these to be equal to 180. So that must mean I need to add 2x on to get that angle there. So how have they written it out? Let's just delete this so we can read. So OBA equals 90 minus x, yeah, and OAB equals 90 minus x because angles in an isosceles triangle. BOA is 180 subtract 90 minus x plus 90 minus x. So 180 subtract 180 minus 2x, and then they've worked it out. So what they've done then is they've said they all must sum to 180, and then they've taken away the 90 minus x added to the 90 minus x, which is exactly the same as what we did. So if you multiply out this bracket, then you get 180 subtract 90, then you're taking away a negative, so this will be add x subtract 90, and then negative 1 times negative x would give you a plus x again. So if then we tidy this up, 180 subtract 90, subtract 90, 0, and x plus x leaves us with the 2x that was required. Last question, question 9. AC and BC are both tangents to the circle. So we know then that these lengths must be equal. Calculate the length of PC, state any assumptions you make. Now PC goes from the circumference of the circle to the point at where the tangents meet outside. We've got radius meeting a tangent, so we know that these are 90 degrees. Now the sneaky thing to notice here is that we've got a right angled triangle, we've got two sides of the triangle, and we're wanting to find, well actually we're not wanting the whole length here, but it will help us out because we know that this length here is a radius of the circle, so that must be equal to the 8 there. So if we can find this whole length from O to C, we can subtract the 8 off, and then we've got our length P here. So we're going to use Pythagoras' theorem to work out the length O to C. So O to C then will be, so remember it's the two shorter sides squared and added together, and then we take the square root. So if we work this out, this gives us the square root of 64 plus 144. So this gives us the square root of 208. And if you work that out, this comes out as 14.4 centimetres. And if you subtract the 8 off, we get that the length we're after was 6.4 centimetres, which is what they've got. And we're just assuming that this length here is given to two significant figures, but we were looking for this answer of 6.4 here. Okay, so are you ready to progress? Yes, your knowledge recall won't be looking at the proofs, it will more be just looking at your knowledge and checking that you're happy and have recalled all of the circle theorems that we've shown you. Okay, so please have a go at the knowledge recall, and then you've got a lesson on direct proportion to do. Good luck.